Okay, well, I'm excited to talk about some of my research, field research that I've done in Greenland for the last couple of years. And yeah, this picture here on that you're looking at is me and Jing Zhao, who's also on the call. Well, we are recording data from one of the Firn cores that we collected from the Greenland ice sheet. So I thought I don't know how much background the audience has, so I'll start pretty broad, and then I'll go very deep into the nerdy details of the research. But if this might be extremely familiar for a lot of you. But anyway, so why go to the Greenland ice sheet in the middle of winter when it's cold and miserable? Well, it's actually quite wonderful, but still, it's definitely hard to collect this kind of data. And the reason is, of course, that the Greenland, okay, that doesn't work. Here we go. The Greenland ice sheet is losing mass. And it's one of the main contributors to the current sea level rise globally. And this picture, or this figure here is from a recent paper by Asa and others, where they have looked at the GRACE mission data of mass loss from the Greenland ice sheet. So this is the total mass loss over time. And what I love about this new figure here is that you can also see the GRACE follow-on mission. And then they have bridged the gap when there was no satellite to measure gravity anomalies with model data. So you can kind of see that this decline that we've seen over the last couple of decades, it is indeed continuing to this day. And because the Greenland ice sheet is, I mean, it's the second largest body of ice on Earth after Antarctica. So if all of it would melt, it would raise global sea levels with, on average, 7 meters. So it's of enormous importance what's going on on the Greenland ice sheet. So what controls the mass balance of Greenland? Well, essentially, it's just 3 main processes or inputs and outputs. First, we have snow accumulation. So here's a little video from my fieldwork. We see snow blowing around here. So that's the main input of mass to the Greenland ice sheet. And then there's 2 ways that the ice sheet is losing mass. And one of them is ice discharge, which we're seeing here. This is like just the coolest video ever of a calving outlet glacier from Greenland. And so what you're seeing here is the ice flowing out into a fjord, and then big icebergs break away and flow out into the ocean. So this is one of the main ways that the ice sheet is losing mass and adding fresh water to the ocean. And then we have the thing that I'm studying, which is runoff. So here is a little drone video from one of our field sites. I also study meltwater outflow. Now I'm going to just talk about something else today, but we have some, this from a study area in Greenland where we look at meltwater outflow on the tundra. So here you see meltwater coming off, and then in the background there you see the Greenland ice sheet, and that's where all this water is coming from. And here you have the surface of the Greenland ice sheet close to the edge, and you'll see here these like blue melt ponds, and up here you have a lot of melting going on. Water flows into ponds, to rivers, and eventually reaches rivers and lakes on the tundra and goes to the ocean. So these are sort of the 3 main components: input from snow, and then losses from ice discharge and runoff. All right, so in none of these I talked about Firn, and I'm actually also going to define Firn for you, but the reason it's interesting and important to study Firn is because it can influence the amount of runoff. And so how that works, I'll explain now. But first, why should we care about Firn? The reason is because not all of the melting that occurs on the surface of the Greenland ice sheet reaches the ocean. Quite a large amount, almost 45% according to our models, suggests that that 45% of the surface melt, just instead of flowing off as a runoff, it infiltrates into the Firn where it refreezes. And so what is Firn? Well, let me show you some stuff from my Intro to Physical Geography. So first we have snow, right? This fluffy, nice material, and when it's deposited, it contains a lot of air in it. Now imagine on the ice sheet, you're gonna have snow upon snow upon the snow. So the snow below this layer, if you go from the top to the bottom, or deeper down into the snow column, you're gonna see that the snow is gonna lose some of its porosity and features and become more and more compacted until it becomes ice. And ice is defined as the material where the pores are closed off. And in between snow and Firn, in between snow and ice, we have Firn. So Firn is snow that survived more than one melting season. And what's so interesting about Firn is that it's a porous material. So meltwater can actually infiltrate below the snow layer, below the winter snow layer, and refreeze in the Firn. And sometimes if you have a lot of meltwater, it can form ice layers there. And yeah, and it can go deep. It can meltwater from the surface. There's studies that show it can reach 10 meters below the surface. So quite a lot. All right, so where do we have Firn? Well, I'm gonna show you some beautiful drawings that I did of a schematic of the Greenland ice sheet, a cross-section of the Greenland ice sheet and the tundra on both sides and bedrock below it. Now, you can divide the ice sheet basically in two zones, and it's the ablation zone and the accumulation zone. So what's different about these two zones is that in the ablation zone, you have more melting than snow accumulation. So you have a net loss of mass, and the accumulation zone is the reverse. Firn is found in the accumulation zone, and it can be up to 80 meters thick, which compared to the ice sheet isn't much, which is because that ice sheet reaches almost 3 kilometers, about 3 kilometers at its highest point. But still, it's quite a substantial amount when you look all over the surface of the ice sheet on the accumulation zone. So there were some really interesting studies that I want to share with you that kind of explains why it's so interesting or important to study Firn. And the first of these studies was published by Joel Harper and others in Nature in 2012. In their study, they did some calculations to estimate like what is the capacity of Firn, since it's a porous medium, what's its capacity to absorb increased melting through the 21st century. And in this paper, they show that the Firn has the potential to buffer sea level rise for decades, which sounds amazing. It's like this giant sponge that could just like soak up the meltwater. Well, something else happened in 2012. It was a huge melt year in Greenland, like one of the record melt in the satellite era and even going back in history. And almost 100% of the surface of the ice sheet experienced surface melting. And I don't think it's wrong to say that this year just changed our whole perspective on the Greenland ice sheet. And after, there were a couple of studies that showed something very interesting that happened during this extreme melt year. And one of those studies was published in Nature Climate Change by Horst Mahgut and other people. What they found, they went out to Greenland in an expedition very similar to the ones that I've done the last couple of years with a small team and drilling Firn cores going down about a couple of 20 meters or so and taking those up to the surface and analyzing what they look like. What they found when they pulled up those Firn cores were very thick layers of ice which they later called ice slabs. And they also found evidence for that those ice slabs had made an impervious layer on top of the porous firn. So the meltwater, subsequent meltwater, couldn't infiltrate through those ice slabs to the porous firn. And instead, all this meltwater that Harper and others were calculating could be soaked up in this porous firn would instead form surface runoff, would flow into channels and swamp zones and eventually reach the ocean and increase the mass loss from the Greenland ice sheet. So essentially these ice slabs would then turn off this capability of firn to soak up this meltwater. And last year, Mike McFerrin published a paper in Nature where he showed that these very thick layers of ice just below the surface of the ice sheet would have actually a significant impact on global sea level if they continue to expand according with the model projections in the 21st century. So these are the reasons why it's interesting to study firn, because it can really influence global sea levels eventually. If these impervious layers of ice, if we have development of these very thick ice layers and they're able to cap up the porous firn below it. So in my research, I've looked at the spatial variability of ice layers in firn and also how it changed over time. So the study area for my work is Southwest Greenland. And here's a detailed image showing the 5 sites, all of them with interesting names. I'll just point out a couple of things here. So these are the core sites we visited in 2017 and collected firn cores. So this is what I'll present. And these sites are the furthest apart, site B and EKT, are about 100 kilometers away from each other. And the elevation distance is about 400 meters. So the difference in elevation is about 400 meters. And yeah, let me show you a short little video of our team collecting cores. So here you see how the team is inserting a barrel attached to extension cords into the ice sheet. And then you put a very heavy drill on top of it. And then use this drill to push that barrel down into the firn. And the barrel is hollow, so it'll fill up of firn material. And here it's pulled up. And what we're going to do now is just push out what's inside here. So you can see how it's kind of hollow. And then you have this firn inside it. Push it out on a tray. And then we can analyze what's in there. And here's a photo to show you some pieces of firn cores. So they're about, I put them here, arranged them to kind of illustrate what ice layers are. And it's like a gradient. And each section here is about 20 centimeters. And you can see the ice layers very clearly here against the sun. And then as you go, this gradient goes from no ice and all firn to all ice. So as we have pulled these cores up from the deep of the ice sheet, we have looked at the ice layer thickness and where those ice layers are. We also measured density. We go down about 20 meters, which in this part of Greenland is about, is firn that has been deposited in the last 31 years, approximately. So, all right, let me show you what we found here. So here is a figure to visualize the contents of this ice core. I'm just going to explain this figure. This is the highest core. So you see the core is from the surface down to 20 meters. And this black line is showing density. And the red line is just there for reference. You can see how the density is increasing with depth. And this is because of the compaction, because the overlying firn is the weight of it is causing what's ever below it to be compacted. But in this figure, you also see some interesting perturbations. And those line up pretty well with the presence of ice layers. So here I'm going to overlay the ice layers with these blue lines here that shows where they are and how thick they are. So you can see that those three peaks there around 5 to maybe 8, 7 meters below the surface correspond pretty well with the regions of lots of ice. All right, so now I'm going to take you down slope and show you the same kind of visualization, but for the 4 other sites, and show you what happened when we go down in elevation. So here is the next site down, and already here you can see a lot more variability, denser firn, and more ice layers. And this pattern is just increases as you go down. And eventually when you reach the lowest elevation site, it's like a lot more ice than at the highest elevation, and much, much denser. And down here, we see like the thickest ice layers, almost 2 meters. So it's very thick. It was difficult to get up. All right, and we can compare this with model simulations to see what the models suggest. And so here's model simulations of snow accumulation at these sites, also arranged in the same kind of elevation order. So this figure is obviously doesn't show any trend whatsoever. This is just here to show you that snowfall or snow accumulation is pretty much identical at these sites. This is the average over the 31 years. What's not identical is how much meltwater is formed on the surface and then goes to refreezing. And that's shown here in red bars. So pretty much all meltwater here goes to refreezing. All meltwater, according to the model, will actually infiltrate and refreeze. And so this model is very consistent with our observations. You can see huge increase in amount of meltwater refreezing at site B compared to EKT. It's about double. So, and you see the same kind of big difference in the cores as well. Okay, all right. So one of the most amazing things about this work is actually the fact that me and my team were not the first ones here. So I'm just showing this picture of footsteps in the snow to kind of illustrate that we are walking in the footsteps of giants here. Obviously, those footsteps are no longer visible on the surface. But anyway, there were other teams here 20 years ago, 30 years ago, and they have saved their data and shared it with us, and we can compare it to look at change over time, which is pretty amazing. And specifically, it's at 2 locations. At Site J, there was a Japanese team in 1989, led by Takao Kameda. And then we have another team, part of the Park project, led by Ellen Mosley Thompson, that they were there in 98. So I'm going to show you side-by-side comparison of these cores. So here's Site J. This is the core that I already showed you from Site J that we collected in 2017. Here's the same site in 1989. Now, and you can see they're very, very different. Now, if nothing had changed between 1989 and 2017, you would expect 2017 core, the top 20 meters, to look somewhat similar to 1989, but it doesn't. Although there are differences in sampling here, the picture is pretty clear. There's a lot more ice in 2017, a lot more blue, which is the ice layers, and it's a lot more dense. Same pattern emerged at Die 2. Here are those 2 cores side by side. A lot more ice in 2017 and a lot denser. And this too fits with the model simulations. This is a reanalysis model that simulates surface mass balance. So here again is actually snowfall at the 5 sites, now shown as a time series. And each line represents one of these sites. Of course, you cannot distinguish the lines from each other because they're all pretty much the same. And so they have the same variability. All right, I'm overlaying here these black lines to illustrate the 31-year period before the sampling of each of these cores. This is the time period that actually where the mass balance is creating the core. So you can see that it's very, very similar with respect to snowfall. But just like the spatial variability, we see it where we saw snowfall averages similar, but meltwater refreezing very different. It's the same with the temporal trends. So here we go. This is the refreezing over time. And now you can see these 5 sites separate out, but you also see there's a huge increase in refreezing starting in the late 80s, early 90s. And so, which is impacting what's going on in 2017 cores, but not so much for the older cores, DI2 and Site J from 98 and 89, which I also call the legacy cores. So we would expect to see something very different, since all this refreezing is meltwater, is coming from meltwater being produced on the surface. So yeah, all right. Okay, I've done all kinds of statistics on these cores, and I'll just show you a few things here. These 2 figures are showing the fraction of each core that is ice layers, and also the mean density. So the blue bars here show the 2017 cores, and the red bar show the legacy cores. So for both of these properties, you can see that it has a very strong spatial gradient because the sites are organized site B is the lowest elevation, and then it goes to the highest elevation at EKT. So you can see how the amount of ice is just dropping as you go to EKT. At site B, if you look at the scale, it's almost 70% of the core is ice layers. And in EKT, it's less than 20. And you can see how the density falls as you go up in elevation. Here you can also see change over time by comparing the red and the blue bars at site J and DI2. And again, you see this much more ice, much denser Firn in 2017 than in 89 and 98. So same image appears. It's ice is increasing as you go down in elevation, and as you come to more modern times. Okay, one thing I want to also share with you is how the ice layers are transforming the Firn column itself. It's pretty remarkable. So here is, I'm going to show you a model simulation. So it's specifically a very simple model, actually, developed by Firn and Langway. And I use this simple model because it's simple, because this model only considers compaction. It does not simulate ice layers or its influence on density. And this model simulates density. So this means that we can compare the model simulation with the observations to get an idea of how ice layers are changing the Firn column itself. So in the couple of plots I'm going to show you, you will see the model in blue. It's going to be a very smooth line. And then the observations in black, which is I already showed you earlier. So I'm gonna take you through the different cores again here. So here we go. This again, the 5 sites. You see the model in blue, the density in black, and then elevation decreases from EKT to site B. So it's kind of messy to look at all 5 of these. So I'm just gonna block out so we can focus on the 2 extremes. So when you compare these two, it's evident that site B, the density in site B is very far removed from this model simulation that only considers compaction, whereas at EKT is actually not a bad approximation. There certainly are deviations, particularly in the top part, but as you go down to the deeper parts of the core, it's a pretty good fit. I mean, I'm pretty excited about this model. But at site B, not so much. So here, and this is because we see the influence of ice then. All right, we can also look at the legacy cores, and I'm gonna shade out some of the other figures too. So legacy cores are the cores collected in 89 and 98. And then you see the 2017 cores on the other side there. And again, there's this very dramatic difference where in the legacy cores collected 20, 30 years earlier, the model lines up pretty well with observations, suggesting that at this time, compaction is driving the density here. But if you look at the 2017 cores, you see many, many positive perturbations due to the formation of ice layers. So very much transformed Firn column. Okay, so one thing I want to talk about then, which has particular interest, is the thickest ice layers. And here is a figure that shows the maximum ice layer thickness in each core. So I found the thickest ice layer in each core and I plotted them out. And again, the 2017 cores are in blue. The older cores collected by other teams are in red. And so you see the same pattern you've seen with pretty much everything, is that the thickest ice layers is found at the lower elevation, and the ice layers are thicker in 2017 than they were when the legacy cores were collected. So, but what this is interesting is because why I pulled this out is because I can't really show with this research if ice layers are indeed blocking infiltration, but if anything should be able to block further infiltration and cap on the porous Firn below it, it would be, we can start with the thickest ice layers. Okay, so here you can see that at site B, the thickest ice layer is almost 2 meters thick, and then it actually drops quite dramatically. All right, so I did a calculation of how much water is needed to form this ice layer of these thicknesses. And then you have to consider that there is snow there before it's not like 100% filled up by infiltrating meltwater, but because there was some snow there. So so it's not like a one-to-one conversion, but I calculated the amount of water that would need to fill up the pore space to form a layer of this thickness. So imagine like it's all like snow, and then you fill it up with water to kind of create an ice layer. And to do that, you would need, here, this figure shows the water equivalents that you would need to fill up basically the pore space before it was to create an ice layer of this thickness. I hope that makes sense. And so you can see that for site B, it's almost 1 meter, and then it drops quite dramatically. All right, so what I did now is just comparing this with the model simulations, the reanalysis model simulations of how much meltwater infiltrates into the Firn column and refreezes. And to look at the most, I started with just the most extreme situation where using the maximum refreezing observed in the 31 years before the core were collected. So here I'm just showing the 2017 cores here because it just got very messy if I added the legacy cores, but the legacy cores are obviously just you get the same idea from the other cores actually. So so the idea is, the question I was asking is like, is it possible that these ice layers could have been created in 1 year, or do you need multiple years to create them? Because if you need multiple years of refreezing, like meltwater coming from the surface, to create these ice layers, there probably is, you could then argue that definitely these ice layers must at least slow down the percolation for ice layers to kind of build upon existing ice layers. So let me show you the comparison with the maximum refreezing observed 31 years before. So I'm going to just show you that as blue, lighter blue bars next to these water equivalence bars. So here we go. Okay, so you have max ice layer thickness or water equivalent for the fill up the thickest ice layers in dark blue, and then lighter blue is the maximum refreezing observed in any year in the 31 year prior. So what's interesting here is that except for site B, in all years, refreezing actually exceeds the maximum ice layer water equivalence needed to form the thickest ice layer. So site J, die2, site A, and EQT could all have been formed in one extreme melt year. Site B, however, not so much. Here, not even in the extreme scenario, I mean, and this is not even, it's not even likely perhaps that these were formed by the maximum refreezing. Could have been another year, so it's just sort of a thought experiment, but not even using the maximum refreezing in the 31 year prior to formation of this ice core. Can you explain, do you have enough water to create this thickest ice layer? So it definitely suggests that there is a multi-year formation occurring here, where the ice layer has been built up by at least 2 years, but possibly more. And I haven't shown you this, but this at site B is also an ice layer that's formed very close to the surface. It's within 3 meters of the surface, whereas all the other sites, the thickest ice layer is much deeper below the surface. So it's also the place where it's close enough to the surface that it actually could possibly have an impact in capping off the porous firn below it. Okay, another evidence of this going on is actually looking at the number of ice layers. So here's just the number of ice layers that I counted in the top 20 meters in these cores. So this is actually, I love this figure because it's like one of the few figures that doesn't have like a strong like decrease with increasing elevation. So it's sort of different. Again, the data from the 2017 cores are shown in blue bars, and the legacy cores, the older cores, are in red. So what's interesting here is that the place where you have the most ice layers is the intermediate elevation sites at die2. So what's going on here? Well, I think what's going on here is that we see something interesting happening at higher elevation, at EKT, where there's less melting going on. There's fewer layers because there's less melting. However, at the lower site, like site B, you have more melt and more refreezing. And here, the reason you have fewer layers, so, is because these layers are merging. Because the existing ice layer must at least slow down infiltration of meltwater so that ice is formed on top of already existing ice layers. Okay, I'm going to show you one more evidence of change over time, which is, I mean, what's so cool about cores is that the deeper you go, the further back in time you go. So, and actually by just comparing the core, the top part of the core with the bottom part, you can look at change over time. So this is what I'm going to show you now. The top 10 meters of each core is a representative of roughly 14 to 15 years prior to the coring. And then if you go down to the next 10 meters, that fern is then between 16 and 31 years old. So it's slightly more years than the top part, but not so much. So what I would expect then to see with respect to, so what I'm going to do now is compare the ice in the top 10 meters with the next 10 meters. And what I expect is that if we look at the ratio between the top and the next 10 meters, I would expect that if we have a steady state condition where nothing has changed over time, we would have slightly more ice in the bottom section than the top section. So it would be the ratio would be below 1. And this is because the bottom part would have slightly more years and be more compacted. So you'd have more years contributing to that part. If we are in a period of decreasing refreezing and surface melting, we would expect the bottom part to have more ice than the top part, and you would have an even lower ratio. In contrast, what we've seen though is that since the early 90s or mid 90s, there's been an increase in refreezing and surface melting, and then we would expect a ratio above 1. And indeed, that is what we see. So here are all the sites, and here's the mass ratio that is observed in all these cores. Again, 2017 cores in blue, the legacy cores in red. And you can see that all of them have a ratio over 1. There's more ice in the top than in the bottom, showing that this is a recent change. So here we have observational evidence of these dramatic changes occurring in the Earth system as we speak. And you can see the legacy cores display this pattern too, so certainly something's going on for a while. All right, so just I'm going to round off with some take-home points and conclusions. So first of all is just that Greenland ice sheet is a major contributor to global sea level rise and will continue to be so. And that the main contribution is coming from surface melting and runoff. And that, but also what I want to point out, which perhaps not a lot of people are thinking about, is like not all the surface melt reaches the ocean. Instead, right now it's infiltrating and freezing in Firn. And the big question is, are these big ice layers, thick ice layers just below the surface in Firn able to cap off and change this ratio from 45 to perhaps a lower number? And that would mean more meltwater going to the ocean. So certainly what my data shows is a dramatic change over time with denser Firn and thicker ice layers and more ice in the Firn. And I can also see that at lower elevations, ice layers are controlling the Firn density, whereas at higher elevation, you can still see that compaction is the driving force. What still is not, I mean, I couldn't resolve 100% and this is why we can still continue to do research about it. The question if the Firn, these ice layers, these very thick ice layers are able to prevent infiltration and instead route surface melting to runoff instead of refreezing and infiltration, is still an open question. However, what I do see in this data is that we have these very thick of ice built at the lowest elevation, and it's probably created over multiple years, which suggests that it definitely slows down infiltration. But whether or not it will return to runoff is, I would say, still an open question. So that's my talk, and I just want to acknowledge funding from the National Science Foundation, a whole bunch of fantastic collaborators, and perhaps most important is my team at Rutgers. So there's a couple of us when we still could go to Greenland ice sheet. All right, thank you so much, and perhaps there's time for questions. I'm gonna stop sharing the screen, I guess. All right, okay.
Wonderful, thank you. Do we have any questions from anyone?
Should we raise our hands or just shout out?
I think you can just go for it.
All right. Thank you for the talk, Asa. Have you seen, or I guess how close to the surface have you seen a formed ice layer? So you said you haven't seen any areas where refreezing of meltwater has caused kind of subaerial surface water flow where there used to only be percolation. But I guess just based on your field work or what you've seen, how many more summers of really heavy melting do you think are needed before you get ice layers that are forming close enough to the surface?
I mean, I think it's possible that actually I think it's possible that the very thick layer at Site B could have been, and it's close to the surface. Right now it's like about, what is 2.5 meters down, but when we went there in 2017, well, 2016 was pretty high melt, but there's like this, there's going to be the winter snow layer above it, which is expected. But I think that might have been enough to create surface runoff, but I don't have any evidence for it. That's kind of what I want to say. Like it could be, but I don't have the evidence. In later years, we went back in 2018 and 2019, and Jing Zhao, who's probably on this call, she's working on that data now. And there we went to lower elevations, and so we have some preliminary analysis that we can see very, very thick layers of ice near the surface, much thicker than Site B actually. And we have looked at some satellite imagery, and we can see that there in those areas there were surface runoff. So it's not to say it might have been there, but looking at the cores, just the cores in isolation, it's hard to say for sure, I think.
Could I ask a really quick follow-up question?
Yeah.
Have you seen any non-draining lakes that have just completely refrozen? And just anywhere in Greenland?
Non-draining lake that completely refrozen. I have not personally witnessed that, but I have also not been like this. This field work is done kind of above the lake region, so there were no like 8 old lakes that we could see. And then most of my work in the ablation zone is kind of at lower elevations, but I have worked by lakes there, but it's always been in the summer, and then they're all flowing and it's water, and so I have never seen them refreeze. But as far as I mean, just reading the literature, I think there are some that doesn't drain and just freezes over, but I haven't witnessed it.
Okay, well, thank you very much.
Thank you.
How much topography has the ice sheet near those drilling sites, and are they high points, low points, or is there no topography?
It's right where we're drilling. It's very, very flat. There are some like sastrugas, so might be like when you go with a snowmobile, you can totally feel it because so maybe like, you know, half a meter high, but it's very, very flat. There are like gentle topography. Like when you're there, it looks completely flat. But when you look at the digital elevation model, you can see that it's not just a total, you know, smooth sloping surface. There are kind of some very gentle ridges and so on there, but they're almost invisible to the eye.
Well, it would be very interesting to make sort of a profile where there is some topography.
Yeah.
And
yeah, we did in 2019. We actually kind of drilled in sort of a little watershed. So, but we're still working on that data. But that's yeah, totally. Just to look at, so that's some of the stuff we're working on now. And when I say we, I mean Jing. In looking at the small scale variability, we did drilled ice cores, like several ice cores, like spaced 10 meters apart to just look at how much does it vary in a small area, and then also like what could be the impact of topography.
Do we have any other questions?
Hey, Asa, can you hear me?
Yes.
Okay. I just switched over to microphone. Leading on that last one, thanks for the great talk. I liked seeing the historical cores as well. On that last point, do you have any sense for the continuity among layers? Because if we're talking about permeability, and you're saying Jing was going to get some 10 meters apart, that might get a handle on that.
Yeah, maybe Jing could give like a part 2 later. She could, so you still have some open slots. Yeah, so we have from the preliminary work of Jing, we can see that there's this thickest layer, like when you look at the cores that was spaced like 10 meters apart, if you can find sort of some of the thickest layers seem to go across. You can follow them across space, and you can also see at Die 2, which is just an amazing place to work at because there's been so many studies there. There's actually you can actually almost create a time series of cores. From our expeditions, we collected cores 3 years in a row there, and the other expeditions collected cores as well. And so you can look at change over time, like over the last decade or so, and you can follow the thick layers just go down. Although, you know, obviously you're not drilling at exact the same site. So there is some continuity you can see in the thickest layers, but all the thinner layers, no, it's just much more random.
Thanks.
Hi, this is Dorothy Petit. Thanks for the talk. That was great. What role do you think that sublimation plays? How big is that? Yeah.
It's pretty small. Like, of course, I only know this from the models, and it's small. It's like if you like sublimation is just I don't know, a few percent of the snowfall. So I think it's small.
Okay, thanks.
Yeah. All right. I think Robin tried to say, yeah.
Yeah. Hi, Asa. I was wondering how you think what you found here really extends to the rest of the ice sheet and the different hydrologic systems we see around the ice sheet, like the predominance of the aquifers on the east side. And some places you see aquifers, some places you see surface lakes. And how do you think this fits into what you're learning fits into the whole mass balance question?
Yeah. I mean, I think, yeah, I think, thanks for that. So I think, well, I think it's, from looking at the literature, it seems to me that aquifers and these ice slabs, thick ice layers, are sort of formed in different regions, like where you have aquifers, where you have high, very high snow accumulation and also melting. So there's enough snow to kind of insulate those aquifers. And there, perhaps you wouldn't expect to see these thick ice layers because they doesn't, I guess it doesn't freeze the same way. So it's like on the southeast coast, it's like, it seems to me, where you have like all these, a lot of those aquifers, and then more on the southwest coast, and actually across, north as well. Like you can see these ice slabs expanding. That's how I recall like Mike McFerrin's work, for example. And it's above, it's like in this, and I think where they would be important is just in this transition zone from just above the ablation zone and the lower part of the accumulation zone. And I actually sort of wonder, because the thing is like right there too, it's the potential for Firn to store increased meltwater is not going to be as big as interior. So when like Joel Harper did his calculation, it was that he considered the whole ice sheet, you know, and the Firn in the whole ice sheet. But in fact, it's going to be this transition zone in the lower elevations where there's already not perhaps that much buffer capacity of the Firn. But certainly there are some studies looking in the Kangerlussuaq region where they're arguing that because of increased melting at higher elevation, which perhaps this part, like this lower part of the accumulation zone, could essentially turn into a runoff zone, so to speak, temporary in big melt years perhaps, or a year after big melt years. And then it, they did some there was a study looking at 2012 specifically, and they estimate that about 10% or so of the melting came from those higher elevations that normally did not like contribute to runoff. So it's like, I think it's like this variable, it's like the runoff producing areas might expand after, or perhaps during big melt years, up into this region where you might find these ice slabs. I don't know, does that kind of get to it?
No, it's nice. You sort of describe how there's a spatial place.
Yes.
In a cross section and around Greenland where this process.
Yeah, and it's gonna vary because some years we're gonna have big melt, like 2019 was a big melt year, but you know, after 2012 was a big melt year, but the year after 2013 was not. So things are going to vary, and we can certainly see like 2016 was pretty big melt year too, and then we went into the field in 2017, 2018, and 2019, and through those years there was no big melt before our field season, and you could see the Firn column, the porous Firn column building up. So there was a creation of porous Firn near the surface at all our sites. All right, okay.
Sorry, I have to head off.
All right.
I'm going to leave it open so you can continue the conversation.
All right, well, thank you.
Thanks for your talk.
Yeah. Well, it's nice to see so many familiar people, actually. Thanks
even if they're mostly snowball. Thank you very much, Asa.
Thank you. All right, anything else? This is it.
Oh, thanks, Asa. How you doing?
Good.
Well, I didn't know anything about Firn before this, so this is usually helpful.
Now you know more than you want to.
Yeah.
Yeah, sorry. Do you have a question or?
Oh, no, my mind's.
It's fine. You don't have to, but you know, I'm actually thinking. I'm like, Mike and I, we went to grad school together. Actually, now it's just my team here, so they'll enjoy this. But I often think back, I wish I was better at Mike Celia's groundwater class.
Well, yeah, I mean, you had all
You
the
could use
terminology right. I mean, it was quite, and yeah, I was surprised at how, yeah, I mean, the Firn is something that is porous media. I never thought of it the sort of analog, so it's
I know,
quite interesting.
right? This is interesting because it's the same, like it's water, just in
Yep.
different phases.
So I'm sorry if I missed it, but have you included some of these processes in some of the GCMs yet, as of yet?
I have not done so, and actually I don't think anyone has. There's still, because I think the GCM stills are pretty like crude when it comes to looking at surface melting and so on. But there's a lot of work working with regional climate models, and because I mean, obviously easier to work with, and they're more. So there's a lot of work trying to understand how you can like compare like different modeling schemes within the regional climate models and how they can be improved. And that's kind of one of the, I mean, most of our work that I do in my group is like, essentially is like, how good are the models and what are we missing? And yeah.
That's great. I mean, I think Craig and they just sort of funded on the sea level rise proposal from NASA. So yeah, it's a good time because I think Model E will be sort of moving in that direction of improving its realism of sort of ice. And Gavin's working on some new hires on ice sheets dynamics and whatnot. So
oh, cool.
I think it's a good time. If I'm not mistaken, there will be at least 2 hires in that general area. So
whoa. I'm like, is it, and they're still happening, like despite the pandemic?
yeah, well, there was a hiring freeze, but then the Columbia said if the hire can work remotely, then you can still bring them on board. So
Okay. All right. Well, that's nice. Well, should hire some people from my group. We're all hydrologists and climatologists.
yeah, actually, well, I don't know what the stage of their hiring is, but we should get the link to you in case there's some overlap of the employment announcement.
Yeah.
I'll send you an email with
Sure.
that.
Yeah, we're thinking about looking at Model E for looking at atmosphere ice sheet connections, but on another idea, but we'll see.
Okay, so I'll send that along to you.
Yeah, sounds great.
I'm a total amateur in this field, but what I wondered, if those ice layers get thick enough and percentage-wise more and more, how they may actually influence the rheology of the ice sheet.
Yeah.
So there may be more stiffness in the upper layers where they are, and I just wonder how the whole mechanics may change as the ice moves down.
I don't know. Yeah, I don't know, because maybe if it's like less, if I could imagine that now it's probably maybe insignificant, but maybe, I don't know, it might have, if it's, because the porosity might be different, or the pore, how much ice, muddy air bubbles you have might be very different compared to ice.
That it may come to the point where actually an ice layer may brittly break while the substratum still viscously flows.
Yeah.
I mean, it's just sort of a thought.
Yeah.
And
yeah.
may, you know, have an influence on the lateral continuity of impermeability. Anyhow, it's just
I also seen like some papers looking at this concept of cryohydrological warming, but that's like from latent heat release, and when you have meltwater, more meltwater percolating into the ice. Maybe not so much in the Firn area, but in lower down in the ablation zone, where you have like these moulins, the vertical conduits, and if you have more meltwater going into cracks and yeah, sounds good, Mike. And could actually make the ice sheet warmer too, and that would change its flow properties. I don't know. But
what is that Swiss institute that looks at the rheology?
Is that age or I don't know. I don't know actually.
They have worked an awful lot on the rheology, different ice.
Yeah, I'm definitely not an expert on it, but I think it's like, because I've read something that, you know, the Holocene ice is different from the older ice, and that actually is affecting the flow somehow.
Okay, I'm signing off.
All right, thank you so much. All right.
Bye-bye.
Yeah, okay, so now soon it's just my loyal team members. I don't know, anyone else have a question? Or Patrick, hello. How's it going? You're still alive, that's wonderful. Hey.
Yeah, I'm actually thinking about, Elizabeth Fisher was working with putting a new snow model over ice sheets in the GIST model. So I'm thinking about looking into refreezing. Yeah.
Oh yeah,
So.
Cool. So yeah, Mike should, I was thinking about you when Mike Puma asked this question, like this is for Patrick. But whatever. All right, do you have any questions or anyone else? Any more questions? How are you doing? You hanging in there?
Yeah, I'm good. How about you?
Yeah, I just came back. I was in Boulder until like last Friday, and I just drove back, and it's so shocking to be back in New Jersey because it's like so much more people. It's frightening actually, but I mean, I just have to get used to it. So, yeah. Anyway, I guess if there's no more questions, just thank you everyone for those. No, it's like just the people I paid to listen left almost. All right. Okay, well, thank you all for tuning in, and I guess take care. Bye.